And now in this lecture we'll find out the area of the circle. In the drawing we have quadrilateral ABCD. Inside this quadrilateral we have a circle, and we also know that line segment AB equals to 2 units, line segment BC equals to 8 units, line segment DC also equals to 8 units. This angle DCB equals to 90 degrees, and this is angle ABC that is also equal to 90 degrees. Our mission is to find out the area of this circle. So first of all we will do a construction. That's to say, we will extend side DA and side CB until they touch each other. Okay. We'll define the touching point of side DA with side CB as M. Side CB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. And then when we extended the straight line CB by a straight line, the result is MC. When you extend the straight line by a straight line, the result must be a straight line. So MC, this line segment MC is a straight line. So if you focus on the upper side of the straight line MC at point B, the sum of the angles must be equal to 180 degrees. So which angles we have? This angle equals to 90 degrees plus the missing angle. Again, at the upper side of CM at point B, we have this angle that is equal to 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of MC at point B to 180 degrees, the missing angle must be equal to 90 degrees. So actually angle ABM equals to 90 degrees. We define angle AMB as theta, and we focus on the right triangle ABM. In this right triangle, this angle equals to theta. This angle equals to 90 degrees. Therefore, this is the missing angle that must be equal to 90 degrees minus theta. So write it down. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big triangle, the big right triangle MDC. In the big right triangle MDC, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. In the next step, we'll prove that the small triangle MAB is similar to the big triangle MDC. Okay, so the big triangle is MDC, and it is similar to the small triangle MAB. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle DCM in the big triangle this angle DCM in the big triangle equals to this angle that is actually angle ABM in the small triangle. They're both equal to 90 degrees, therefore they are equal to each other. Repeating again. Angle DCM in the big triangle equals to angle ABM. They're both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles. Therefore, we can say that angle theta equals to itself. So we can define angle theta as angle DMC. When we see it as it belongs to the big triangle, DMC. And it is equal to himself. We can define angle theta also as angle AMB. And then angle theta belongs to the small triangle. So those are two different names to the same angle, angle theta. Repeat again. Angle theta is angle DMC, and angle theta can equal to angle theta also angle A and B. So angle theta equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle CDM in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle CDM in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big triangles are correspondingly equal to all the three angles in the small triangle. Therefore, we actually proved that the big triangle MDC is similar. Triangle DCM is similar. This is the sign of similar to the small triangle MAB. According to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all the three angles in one triangle are correspondingly equal to all the three angles of another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule, exactly as we proved about these two triangles. And from the fact that the two triangles are similar to each other, we derive that the following relationship exists between their sides. We conclude that side MC in the big triangle over side MB, the small triangle, equals to side DC in the big triangle. This is side DC over side AB in the small triangle. Repeat again. MC over MB equals to DC over AB. MC from the drawing is very easy to see that the length of side MC equals to MB plus BC. MC equals to MB plus BC, that is 8. So in total, MC equals to MB plus 8. So we can substitute MC by MB plus 8. MC equals to MB plus 8 over MB, and it is equal to DC equals to 8 over AB equals to 2 according to what is given us in the question. So if we've already found out that MB plus 8 over MB equals to 8 over 2 is 4. Okay, MB plus 8 over MB equals to 4. We'll multiply this equation by MB, and finally we get that MB plus 8 equals to 4 times MB. We subtract MB from this equation, and we get that 8 equals to 4 MB plus MB, it is 3 MB. 8 equals to 3 MB. We'll divide this equation by 3, and we get finally that MB equals to 8 over 3 units. So here we can write down the original drawing with the length of line segment MB. It is equal to 8 over 3 units. In the next step, we'll implement the Pythagoras theorem on the small right triangle, triangle AMB. Here, by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle AMB is AM, therefore the square of the hypotenuse is AM squared. Must be equal to AB squared plus MB squared. Repeat again. According to the Pythagoras theorem, in the right triangle AMB, AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB equals to 2, therefore AB squared is 2 squared, that is 4, plus MB squared. We just right now found out that MB equals to 8 over 3, therefore MB squared is 8 over 3 squared. So AM squared equals to 4 plus 8 over 3 squared, it is equal to 8 squared, that is 64, over 3 squared, that is 9. In the next step, we will multiply 4 by 9 and then we divide it by 9 in order to have common factor with 64 over 9. So am squared equals to 4 times 9 is 36 plus 64 over 9. 36 plus 64, it is 100 over 9. In the next step, we took the root out of this equation and finally we get that am equals to the square root of 9 over 100. The square root of 100 is 10 over the square root of 9 is 3. So in conclusion, we found out that the length of the hypotenuse am is 10 over 3 units. So we can write down in the original drawing that the length of line segment am is equal to 10 over 3 units. Okay, so in the next step I present to you rule number 1 and we'll implement rule number 1 in our drawing. But before that, you can see here that side AB is tangent to the circle at this point. So we define the point of tendency of AB with the circle as M. Here, line segment BC is tangent to the circle at this point, so we define the point of tendency of line segment BC with the circle as N. So the next step I present to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have AB, line segment AB is tangent to the circle at point M. Point M is the point of tendency. Point O is the center of the circle, therefore OM is the radius of the circle. Here, the radius OM is drawn to the point of tendency, that is to say it is drawn to point M. That is the point of tendency of tangent AB with the circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to the radius. That is to say, in this case, tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, which means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. According to this rule, rule number 1. We can implement rule number 1 in our drawing. We define the center of this circle as O. We join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that we define as X. Again, you can implement rule number 1. Why? Because the radius OM, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. In the next step, we join points O and N together by a straight line. Point O is the center of the circle. Point N is the point of the circle itself. Therefore, ON is the radius of the circle that we define as X. Again, the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent BC with the circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. In the next step, we'll focus on quadrilateral NOBN, and so here we have 2 points with the same letter. This is actually, this point is point M. So we have quadrilateral MOBN. We focus on quadrilateral MOBN. Inside this quadrilateral we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Therefore, this fourth angle must be equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So 270 degrees plus 90 degrees is equal to 360 degrees, exactly according to the rule that I mentioned. Okay, so in the next step, we draw perpendicular on BC in such a way that it will be also tangent to the circle. So this is a perpendicular, therefore this angle equals to 90 degrees and this angle equals to 90 degrees. We define the touching point of the perpendicular with BC as G. As already mentioned before, the perpendicular is also tangent to the circle at this point. We define the point of tendency of the perpendicular with the circle as point L. Actually, it is absolutely possible to draw perpendicular on BC that it will be also tangent to the circle. Why? Because if we draw the perpendicular on the farthest point from the center, then the perpendicular also will be tangent to this circle. Okay? In the next step, we'll join points O and L together by a straight line. Point O is the center of the circle, point L is the point of the circle itself, therefore OL is the radius of the circle that we defined as X. Again, we have the same rule. The radius OL, it is drawn to point of tendency, that is to say it is drawn to point L, that is the point of tendency of GL with the circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DL will be perpendicular to the radius LO. So if GL is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also will be equal to 90 degrees, according to rule number 1. We focus on quadrilateral OL and G. Inside this quadrilateral we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees, according to the rule that I mentioned, that the sum of the angles in any quadrilateral is equal to 360 degrees. So OL is the radius of the circle that is equal to X. OM is also the radius of the circle that is equal to X. The two radii touch each other at point O. LX, it is absolutely, LO, it is absolutely a straight line, because it is the radius of the circle. MO, it is absolutely a straight line because it is the radius of the circle. The only question that is left to answer is whether if at their touching point they create a straight line. If at their touching point they create a straight line, it means that ML in total is a straight line. So what happens at their touching point, that is to say at point O, what happens at the touching point of the two radii with each other? Actually at their touching point, that is actually point O, they create between them angle of 180 degrees. And because of the fact that at their touching point we have angle of 180 degrees, that is 90 plus 90 is 180 degrees, any angle that is equal to 180 degrees must be a straight line. Therefore, at their touching point, we have one straight line. That is to say, the two radii touch each other at their touching point in such a way that they create one straight line. Okay, therefore, ML is one straight line that consists of the two radii with each other. Therefore, ML must be the diameter of the circle. We can also give another explanation that because of the fact that their touching point, that is to say at point O, we have angle of 180 degrees, it means that MOL must be a straight line because this angle equals to 180 degrees. So we have here line segment MN that passes from the center of the circle and touches the circle at points M and L. So it is chord ML that passes through the center of the circle, that is to say from point O. Any chord that passes through the center of the circle must be the diameter of the circle, and for that reason ML is the diameter of the circle. So we can write here that ML is the diameter of the circle. ML is the diameter of the circle. In the next step, we'll focus on quadrangle MLBG. Inside quadrangle MLBG, we have 1, 2, 3, 4 right angles. Any quadrangle that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrangle MLBG as a rectangle. Quadrangle MLBG is a rectangle. And we also note that the opposite sides of a rectangle are equal to each other. That is to say, ML equals to BG. Again, ML equals to BG. ML side ML equals to side BG. Rectangle MLBG, but we just write down found out that ML is the diameter of the circle. ML is the diameter, and from this equation BG equals to ML equals to the diameter, we will derive that BG is also the diameter of the circle. Here BG is the diameter of the circle. The diameter of any circle is twice as long as the radius, and the radius of this circle equals to x. Therefore the diameter must be equal to 2x. That is to say BG equals to 2x. VG equals to 2x in its length. Okay. In the next step, we will extend the perpendicular GL until it touches side MD. We define the touching point of the extended GL with side MD is T. By doing this construction, we created here the right triangle TMG. In the right triangle TMG, the big right triangle TMG, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta, as I already explained it previously. In the next step, we'll prove that the big triangle MTG is similar to the right triangle MAB. Again, the big triangle MTG, the big right triangle MTG is similar to the small right triangle MAB. So I write it down. Triangle MTG is similar to the right small triangle and MAB. So all those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So I can write down that angle TGM in the big triangle is equal to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again. Angle TGM in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, therefore angle theta equals to itself. So we can define angle theta as angle TMG when we relate to angle theta as it belongs to the big triangle, and it is equal to angle theta itself, so we can define angle theta as angle AMB when we look at angle theta as it belongs to the small triangle AMB. Repeat again. We have two different names to the same angle, angle theta. This equation means that angle theta equals to itself. Angle theta is a common angle that belongs to both triangles. Okay, and finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle MTG, the big triangle, is equal to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. angle MTG in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees on the theta, therefore they are equal to each other. So we actually proved that all the three angles in the big triangle are correspondingly equal to all the three angles in the small triangle. Therefore, we actually proved that the big triangle MTG is similar to the small triangle MAB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that MG in the big triangle over MB in the small triangle equals to TG in the big triangle over AB in the small triangle. Repeat again. MG over MB equals to TG over AB. What is the size, the length of MG? From the drawing it is very easy to see that MG equals to MB plus BG. That is to say MG equals to MB, it is 8 over 3 plus BG is 2x. So in total MG equals to 8 over 3 plus 2x. So we substitute MG by 8 over 3 plus 2x over MB, it is 8 over 3, and it is equal to TG. TG is the missing side, so we leave it as it is, over AB. AB is 2, so we substitute AB by 2. So we found out that 8 over 3 plus 2x over 8 over 3 equals to TG over 2. Here we multiply 2x by 3 and then we divide it by 3 in order to have a common factor with 8 over 3. And we get that 8 over 3, 2x times 3 is 6x over 3 over 8 over 3 equals to TG over 2. Here, this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and finally we left with 8 plus 6x over 8 equals to TG over 2. Okay, so in the next step we will of course multiply this equation and we will get that two times 8 plus 6x equals to 8 times TG. Okay. Here we divide this equation by 2 and we will get that 8 plus 6x equals to 8 over 2 is 4. So 8 plus 6x equals to 4 TG. The next step we divide this equation by 4 and finally we will get that TG equals to 8 over 4 is 2 plus 6 over 4 is 1.5. 6x over 4 is 1.5x. So in conclusion, we found out that TG equals to 2 plus 1.5x. So we can write down in the original drawing that 9 segment TG or side TG here it is equal to 2 plus 1.5x. Because of the fact that the small triangle MAB is similar to the big triangle MTG, we can derive from it that additional relationship exists between their sides. We derive that MG in the big triangle over MB in the small triangle equals to TM in the big triangle over AM in the small triangle. Repeat again. MG over MB equals to TM over AM. I already explained before that MG equals to 8 over 3 plus 2x. Over MB equals to 8 over 3. And it is equal to TM. What is the length of Tm? From the drawing it is very easy to see that Tm equals to Ta plus Am. That is to say Tm equals to Ta plus Am, that is 10 over 3, so in total Tm equals to Ta plus 8 over 3. So we substitute Tm by Ta plus 8 over 3. Over AM is 8 over 3. So in conclusion, we found out that 8 over 3 plus 2x over 8 over 3 equals to Ta plus 8 over 3 over 8 over 3. Here we will multiply 2x by 3 and then we divide it by 3. And here also we'll multiply Ta by 3 and then we divide it by 3 in order to have a common factor of 10 over 3. We do it now and we get that 8 over 3 plus 2x times 3 is 6x over 8 over 3 equals to 10 over 3. Ta times 3 is 3Ta over 3 over 10 over 3. So in this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. Here also, in the other side of the equation we have 3 in the numerator and 3 in the numerator and 3 in the denominator, so 3 will also get cancelled, and we're left only with 8 plus 6x over 8 equals to 10 plus 3ta over 10. Here we'll cross multiply this equation and finally we get that 10 times 8 plus 6x equals to 8 times 10 plus 3ta. We'll open the brackets on both sides of this equation and we get that 8 times 10 is 80 plus 8 times 6x is 60x equals to 8 times 10 is 80 plus 8 times 28 is 24ta. So here we have 80 on both sides of the equation, so 80 will get cancelled, and we're left only with 60x, that is equal to 24ta. Here we divide this equation by 24, and finally we get that ta equals to 60x over 24 is equal to 2.5x. In conclusion, we found out that the length of line segment TA equals to 2.5x. Here you can write down that the length of this side or line segment AT, it is equal to 2.5x. Okay. In the next step, I'll copy quadrilateral ATGB in a new page, and we'll analyze it. Okay, this is quadrilateral ATBG that I copied from the original drawing. This quadrilateral ATBG blocks this circle, so I copy the circle in our quadrilateral here. The quadrilateral touches the circle at 4 points, or the circle is tangent to the quadrilateral at 4 points. This is the first point of tangency, so we'll define this point as M. This is the second point of tangency between the circle and the quadrilateral. We'll define the point of tangency as N. This is the first point of tangency between the quadrilateral and the circle. We define this point as S. And finally, this is the fourth point of tangency between the circle and the quadrilateral. We define this point, the point of tangency, as L. In the next step, I'll present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Point P is the common external point. From point P, we draw two tangents to this circle. Tangent PA is tangent to the circle at point A, and tangent PB is tangent to the circle at point B. According to this rule number 2, whenever you draw two tangents to a circle from a common external point like here, from point P, then the lengths of those two tangents will be equal. The lengths of those two tangents will be equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing. Why? Because in our drawing, we have the common external point, point A. From the common external point, point A, we have two tangents to this circle, tangent AM and tangent AN. And according to rule number 2, they must be equal to each other. That is to say, AM equals to AN. So if AM is A, then AN must be also equal to A. The next step will focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BN and tangent BS. And according to rule number 2, they are equal to each other. This is to say, BN equals to BS. So if Bn is B, then Bs must be also equal to B. The next step will focus on the common external point, point G. From the common external point, point G, we have two tangents to this circle, tangent GS and tangent GL. And according to rule number 2, they are equal to each other, so GS equals to GL. So finally, if GS is C, then GL is also C. And finally, we'll focus on the common external point, point T. From the common external point, point T, we have two tangents to this circle. We have tangent TM and tangent TL. And according to rule number 2, they must be equal to each other. So TM equals to TL. So if TM is D, then TL must be also equal to D. Okay. So in the next step, we will add side AT and side BG, or this on the other one, AT, BG. So AT plus BG, AT plus BG equals to AT equals to A plus D, so we substitute AT by A plus D plus BG. From the drawing, it is very easy to see that BG equals to B plus C. So we substitute BG by B plus C. So in conclusion, we found out that AT plus BG equals to A plus D plus B plus C. So we can change the orders of the letters here. And it will be equal to A plus B plus C plus D. In the next step, we'll join side AB to side TG. So AB plus TG, what is the value of AB plus TG? AB, it is very easy to see that AB is A plus B. And TG is C plus D. So in conclusion, we found out that AB plus TG equals to AB plus A plus B plus C plus D, but AT plus BG also equals to A plus B plus C plus D. Therefore, AT plus BG equals to AB plus CG. Okay. AT plus BG equals to AB plus TG. We have already found out that AT equals to 2.5x, so we substitute AT by 2.5x plus BG. We have already found out that BG equals to 2x, so we substitute BG by 2x, and it is equal to AB. AB is 2, according to what is given as the equation, so we substitute AB by 2 plus TG. TG equals to 2 plus 1.5x. So we substitute TG by 2 plus 1.5x. So we actually found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x. And it is equal to 2 plus 2 is 4 plus 1.5x. Here we subtract 1.5x from this equation, and finally we get that 4.5x minus 1.5x, it is equal to 3x, and there 3x equals to 4. Here we'll divide this equation by 3, and finally we get that x equals to 4 over 3 units. That is to say, the radius of this circle equals to 4, x equals to 4 over 3 units. And we also know that the area of any circle, here the square bracket is the sign for the area, so the area of any circle equals pi times the radius squared. R is the radius, so it is in our specific circle, it is pi, and the radius equals to x, so it is pi x squared. Pi, but we just right now found out that x equals to 4 over 3, so we can substitute x by 4 over 3, so it is pi, x is 4 over 3, therefore x squared is 4 over 3 squared. So it is pi 4 times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. We can finally found out that the area of this circle equals to 16 pi over 9 square units. Or in terms of numbers, it is equal to 5.585 square units. And that is the answer to the question. In the next step, I will summarize the lecture. In this lecture, we found out the area of this circle. In the drawing, we have quadrilateral ABCD. Inside this quadrilateral, quadrilateral ABCD, we have this circle. In addition, we know that line segment AB equals to 2 units in its length, line segment BC equals to 8 units in its length, line segment DC also equals to 8 units in its length. This angle DCB equals to 90 degrees, and this angle ABC equals to 90 degrees also. Our mission is to find out the area of this circle. So, first of all, we did the construction, that is to say, we extended side DA and side CB until, by set line, until they touch each other. Till the two sides touch each other. They touch each other at this point, so we define the touching point of the two sides of each other as SM. CB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. We extended the straight line CB by straight line. When you extend the straight line by straight line, the result must be a straight line. That is to say, CM is also a straight line. If we focus on the upper side of the straight line CM at point B, here the sum of the angles on the upper side of CM at point B must be equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees. 90 degrees plus 90 degrees, it is 180 degrees. The missing angle must be equal to 90 degrees. So angle ABM equals to 90 degrees. We focus on the right triangle ABM. We define this angle as theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta, it is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. In the next step, we focused on the big triangle MDC. In the big triangle MDC, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. In the next step, we proved that the big triangle MDC is similar to the small triangle ABM. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually proved that all the three angles of the big triangle DCM are correspondingly equal to all the three angles of the small triangle ABM. Therefore, those two triangles are similar to each other according to angle similarity rule. What is angle similarity rule? Actually, if you prove that all three angles in one triangle are correspondingly equal to all the angles of another triangle, then the two triangles will be equal to each other according to angle similarity rule. Exactly as we put in these two triangles. And because of the fact that the small triangle ABM is similar to the big triangle MDC, we derive that the following relationship exists between their sides. That MC in the big triangle over MB in the small triangle equals to TG equals to DC in the big triangle over AB in the small triangle. Repeat again. MC over MB equals to DC over AB. What is the length of MC? MC equals to MB plus BC. That is to say, MC equals to MB plus BC, but BC is 8, so in total MC equals to MB plus 8. So here we substitute MC by MB plus 8 over MB equals to DC is 8 and AB is 2. So this C over AB is 8 over 2. 8 over 2 is 4. So MB plus 8 over MB equals to 4. We multiply this equation by MB. And we found out that 4 times MB equals to MB plus 8. We subtracted MB from this equation and finally found out that 8 equals to 4MB minus MB is 3MB. 8 equals to 3MB. We divided this equation by 3 and finally found out that MB equals to 8 over 3 units. So the length of line segment MB is 8 over 3 units. Then we implemented the Pythagoras theorem on triangle ABM. On this triangle ABM, according to the Pythagoras theorem, AM squared equals to AB squared plus BM squared. Repeat again. In the right triangle AB, AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB is 2, therefore AB squared is 2 squared, that is 4, plus MB squared. MB, just right now found out that MB is 8 over 3, therefore MB squared is 8 over 3 squared. So AM squared equals to 4 plus 8 over 3 squared. 8 over 3 squared is 8 squared, that is 64, over 3 squared, that is 9. So AM squared equals to 4 plus 64 over 9. Then we multiplied 4 by 9 and then we divided it by 9 in order to have a common factor with 64 over 9. So AM squared equals to 4 times 9 is 36 plus 64 over 9. 36 plus 64 is 100 over 9. Then we took a root out of this equation and finally found out that AM equals to the square root of 100 over 9. The square root of 100 is 10 and the square root of 9 is 3. So we found out that AM, the hypotenuse AM equals to 10 over 3. So we can write here that the hypotenuse AM, the line segment AM equals to 10 over 3 units. Okay, in the next step I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have tangent AB, that is tangent to the circle at point M. Point M is the point of tendency. And we have the radius OM, that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with the circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule, rule number 1. So we actually implemented rule number 1 in our drawing. We define the center of this circle as O. Point M is the point of tendency of tangent AB with this circle. We join points O and M together by straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that we define as X. So here we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Likewise, we have tangent BG is tangent to the circle at point N. We join points O and N. ON is the radius of the circle that is equal to X according to our definition. Again, we have the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tangency of tangent BG with this circle. And whenever I have a radius that is drawn to the point of tendency, then tangent BG will be perpendicular to NO. So if BG is perpendicular to NO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. We focus on quadrilateral OMB BN, quadrilateral OMBN, we have 1, 2, 3 right angles. Therefore, the fourth angle here must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Then we draw perpendicular on BC in such a way that the perpendicular will be also tangent to the circle at point L. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We join points OL and M together by straight line. OL is the radius of the circle. We have the radius OL that is drawn to the point of tendency, that is to say it is drawn to point L, that is the point of tendency of tangent GT with the circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent TG will be perpendicular to the radius LO. So if TG is perpendicular to LO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So in quadrilateral OLNG we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So at point O we have angle LOM equals to 90 degrees plus 90 degrees, it is 180 degrees. Any angle that is equal to 180 degrees, it is a straight line. Therefore, LM and LOM is a straight line, it means that LM is a straight line. LM is a straight line that touches the circle at points L and M. That is to say, LM is a chord that passes through the center of the circle, that is to say, it is passes through point O, that is the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. Therefore, LM is the diameter of the circle. Here, ML is the diameter of the circle. ML is the diameter of the circle. Then we focus on quadrilateral MLBG. In quadrilateral MLBG we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral MBLG is a rectangle. Quadrilateral MLBG is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, BG equals to ML. Okay. BG equals to ML. The opposite sides of rectangle ML, BG are equal to each other. What we just right now found out that ML is the diameter. From this equation we derive that BG is also the diameter. BG is the diameter of the circle. The radius of the circle equals to x, therefore the diameter must be twice as long as the radius. If the radius is x, then the diameter must be equal to 2x. So the diameter BG equals to 2x. Here, BG equals to 2x. In the next step, we extended the perpendicular GL until it touches side TM at point T. Then we focus on the big triangle TGM. In the big triangle TGM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Then we prove that the big triangle MTG is similar to the small triangle MBM. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, so angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we prove that the big triangle TGM is similar to the small triangle ABM according to angle similarity rule. And from the fact that the two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that MG in the big triangle over MB in the small triangle equals to TG in the big triangle over AB in the small triangle. I'll repeat again. MG over MB equals to TG over AB. What is the length of MG? MG equals to MB plus BG. That is to say, MG equals to MB, that is 8 over 3, plus BG, that is 2x. So in total, MG equals to 8 over 3 plus 2x. So we substitute MG by 8 over 3 plus 2x over MB. MB is 8 over 3, so we substitute MB by 8 over 3, and it is equal to TG. TG is the missing side, so we leave it as it is, over AB. AB is 2, so we substitute AB by 2. In conclusion, we found out that 8 over 3 plus 2x over 8 over 3 equals to TG over 2. We multiplied 2x by 3 and then we divided by 3, and found out that 8 plus 2x times 3 is 6x over 3 over 8 over 3 is equal to TG over 2. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and finally we got that 8 plus 6x over 8 equals to TG over 2. Because multiply this equation, and found out that two times 8 plus 6x equals to 8 times TG. We divided this equation by 2 and found out that 8 plus 6x equals to 8 over 2 is 4. So 8 plus 6x equals to 4 times TG. Then we divided this equation by 4 and finally found out that TG equals to 8 over 4 is 2 plus 6x over 2 is 1.5x. In total, TG equals to 2 plus 1.5x. You can write down here this TG, nice segment TG equals to 2 plus 1.5x. Because of the fact that the big triangle TGM is similar to the small triangle ABM, we derive that addition the following relationship exists between their sides. We will derive that MG in the big triangle over MB in the small triangle equals to TM in the big triangle over AM in the small triangle. I'll repeat again. MG over MB equals to TM over MA. I've already explained to you that MG is 8 over 3 plus 2x, so we substitute MG by 8 over 3 by 2x, MB is 8 over 3, and it is equal to Tm. What is the length of Tm? From the domain it is very easy to see that Tm equals to Ta plus Am. That is to say, Tm equals to Ta plus Am is 8 over 3. So in total, Tm equals to Ta plus 8 over 3. So we substitute Tm by 8 over 3 plus Ta over Ma. Ma is 8 over 3. So Ma by 8 over 3. Here we multiplied 2x by 3 and then we divided by 3, and also we multiplied Ta by 3 and then we divided by 3. And found out that 8 over 3 plus 2x times 3 is 6x over 3 over 8 over 3 equals to 3 times Ta is 3Ta plus 10 over 3 equals over 10 over 3. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. We have 3 in the numerator here and 3 in the denominator, so 3 will also get cancelled. And finally we found out that 8 plus 6x over 8 equals to 10 plus 3Ta over 10. Here of course multiply this equation, and finally we found out that 10 times 8 plus 6x equals to 8 times 10 plus 3Ta. We open the brackets on both sides of the equation and found out that 8 times 10 is 80 plus 8 times 6x is 60x. It is equal to 8 times 10 is 80 plus 8 times 3Ta is 24 TA. We have 80 on both sides of the equation, so 80 will get cancelled, and we're left only with 60x equals to 24 TA. We divided this equation by 24 and finally found out that TA equals to 60x over 24 is 2.5x. So here, this line segment TA equals to 2.5x. Then I copied quadrilateral ATGB in this new page here. This is quadrilateral ATBG that I copied from the original drawing. This quadrilateral ATBG belongs to this circle, so I copied this circle here. Actually, the circle touches the quadrilateral at 4 points. We have 4 points of tangency with the circle and the quadrilateral. The 4 points are M, N, S, and L. Then I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So we have the common external point, point P. From the common external point, point P, we have two tangents to the circle, PA and PB, and according to rule number 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule number 2 in our drawing. Why? Because if you focus at point A, we have two tangents to the circle, tangent AM and tangent AN, and they must be equal to each other, according to rule number 2. So AM equals to AN. So if AM is A, then AN also is A. Then focus on the common external point, point B. From the common external point, point B, we have two tangents to the circle, tangent BN and tangent BS. And according to rule number 2, they must be equal to each other. So BN equals to SB. So if BN is B, then BS must be also equal to B. Then we have the common external point, point G. From the common external point, point G, we have two tangents to the circle, tangent TGL and tangent GS. And according to rule number 2, they must be equal to each other. So GL equals to GS. So if GL is C, then GS must be also equal to C. And finally, we have the common external point, point T. From the common external point, point T, we have two tangents to the circle, tangent TM and tangent TL. And according to rule number 2, they must be equal to each other. That is to say, TM equals to TL. So if TL is D, then if TL is D, then TM must be also equal to D. Then actually added side TA to side BG. What is TA or AT plus BG? AT equals to A plus D and BG equals to D plus C. So in total, AT plus BG equals to A plus D plus B plus C. You can change the order here, and we'll get that AT plus BG is A plus B plus C plus D. Then we added side TG, side AB to side TG, AB plus TG. AB is A plus B and TG is C plus D. So in total, AB plus DG, it is also equals to A plus B plus C plus D. So AT plus BG equals to A plus B plus C plus D, and AB plus TG also equals to A plus B plus C plus D. Therefore, they must be equal to each other. Therefore, AT plus BG equals to AB plus TG. AT is 2.5x, so substitute AT by 2.5x. BG is 2x, so substitute BG by 2x. And it is equal to AB. AB is 2, so substitute AB by 2. And finally TG plus TG. TG is 2 plus 1.5x, so substitute TG by 2 plus 1.5x. And finally found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2 is 4.5x, and it is equal to 2 plus 2 is 4 plus 1.5x. We subtracted 1.5x from this equation and finally found out that 4.5x minus 1.5x is 3x, so 3x equals to 4. We divided this equation by 3 and finally found out x, the radius of the circle, equals to 4 over 3 units. Here, the radius of this circle, x, equals to 4 over 3 units. The area of any circle, so the squared bracket is the sign for the area. The area of any circle equals to pi r squared. R is the radius, so it is pi times the radius squared, pi r squared. In our specific case, our specific circle, the radius of the circle is x, therefore the area of the circle will be equal to pi x squared. We just now found out that x equals to 4 over 3, so we can substitute x by 4 over 3. We did it and we found out that the area of the circle equals to pi times 4 over 3 squared. Pi times 4 over 3 squared, 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in total we found out that the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, the area of this circle equals to 5.585 units. Repeat again, the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. Okay, thank you very much.